So the first thing to note, I've made a note here, and I don't think it's in the book like that. Horizontal transformations, they happen in reverse. Everything horizontally is in reverse. For instance, if it says x take 3, then the shift is actually to the right, whereas you would expect it to go to the left because it's take 3, right? So it's in reverse, it's the opposite. If it says x over 2, x divided by 2, then that is not, it's half of x. But that actually means a stretch by a factor 2 and not a compression. So 2x is a compression. So that would times it by 1/2. Again, opposite to what you would think. And then the other big deal is that shifting stuff in x goes before stretching. Right? So that's sort of adding before multiplying, which in back maths obviously not allowed, but here it does. Now if we keep that in mind, and we just separate x from y, or we keep that separate, things are getting easy. See, here we talk about the function x squared, and that function, as we know, has the origin here. My pen starts to write. Yep, there. And it goes there to 1, 1, and there, and 2, 4, and negative 2, 4, and 3, 9 as well. Yeah. So there's that parabola, like that. And now I want to concentrate straight away on the most difficult one, which appears to be that one there. And I just want to relate the points on the original graph to the new graph that I'm going to do. And I'm going to separate x and y. On the original x squared here, we've got the point 0, 0, for instance, right? Now that point will translate into, well, what happens to x? In horizontal manner, at negative 3, we can see there, so the thing is shifted to the right by 3, and it's x over 2. So according to my note here, it's a stretch by 2. And the shift comes before the stretch. So I take my x coordinate, which is 0, I shift it plus 3, 0 plus 3, because I need to go to the right. And then I stretch it by 2. So this whole lot times 2. And that's my new x coordinate. Same for the y coordinate, but the y coordinate is straightforward. If the y coordinate is stretched by 2, then it's just stretched by 2, and afterwards 4 is added to it. It gets up 4. The y coordinate that we have is 0. I'm stretching it by 2, and then I'm adding 4. So there everything's normal, in the normal order, just like vectors. So the outcome here is 3 times 2 is 6, and this is 0, 4. So I'm claiming that my vertex of 0, 0 ends up in 6, 4. Yeah? And this is a method that really works well if you just keep x and y separate. So the next well-known point that we have is 1, 1, for instance. Where would that end up? Well, 1, 1, it's 1 plus 3 times by 2. That's the new x coordinate, because that's what happens to it. The y coordinate is 1, multiplied by 2 for the stretch, and then add 4. So that ends up in 4 times 2 is 8, comma, 2 plus 4, 6. Let's do one more, 2, 2. 2, 4 are the coordinates. And then the new coordinates are 2 plus 3 times 2. That's for the x coordinate. Again, the shift comes before the stretch, so that's why I use the brackets. And then 4 times 2 plus 4. So the new coordinates are 10 and 12. Now these ones, I can just put in 6, 4 is here, and 8, 6. is then there, and 10, 12, did I do it correctly? 8, 4 is 12, 5 is 10, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12 is there. Now, this thing is symmetrical, so I can use all that. And there's my image. So that's that one. All right? So can you see by stretching it to horizontally and then stretching it to vertically, it actually became apparently a little bit wider than the original x squared. And of course it moved up there and there with a new vertex. Okay?